Hi everyone, my name is Mohammed Latif and I'm going to present our recent work on the growth of massive black holes. To put the things in context very briefly, my motivation for this work comes from the observations of high redshift quasars, which revealed the existence of supermassive black holes of a few billion solar masses within the first giga-year after the Big Bang. How come these objects form and grow to such high masses within the short time of a few hundred mega-year? It's still an open question. Now, if you look at the various black hole formation mechanisms, they predict the black holes of 100 to 100,000 solar masses. In the rest of my talk, I'm going to assume that one of the progenitors of my simulated halo has formed a massive black hole of 100,000 solar masses via direct collapse model, and I'm going to explore its growth via 3D radiation hydrodynamics cosmological simulation. The simulated halo has a mass of 2 billion solar masses at redshift 16. This is the most massive halo in the cosmological periodic box of 25 megaparsec over each in size. Just to remind you that the resolution of my simulation is physical resolution is few parsec and dark matter resolution of 100,000 solar masses. What we do differently from most of the studies in the field is that we self-consistently model both the population 3 and population 2 stars, and we model their radiative and supernova feedback along with X-ray feedback from accreting black hole, which we insert in the most massive progenitor halo at redshift 26 and follow its growth from redshift 26 down to 16. And we basically use a ray tracing algorithm to compute the radiative feedback from each star particle. So our simulations are able to follow the cosmic gas flow from megaparsec scales down to few parsec, which allows us to resolve the boundary radius of a massive black hole. So what we found is the following, as you see in the upper left plot. We found that X-rays from black hole play a dual role. On one hand, they suppress the star formation by heating the gas. As a result, black hole can accrete up to few times 10 to the minus 2 solar mass per year. On the other hand, X-rays promote the formation of molecular hydrogen, which results in a small cluster of few hundred solar masses in the vicinity of black hole. Since this cluster is made of primordial stars or population 3 stars, due to their shorter lifetimes, they quickly go off a supernova. And as a result, the mass accretion rate onto the black hole falls down by an order of magnitude. Later on, the gas cools through the metal line cooling and is able to fall back and get accreted back into the black hole, onto the black hole. This keeps happening during the simulation. So as massive stars die, they generate outflows. And so basically the growth of massive black hole is mainly regulated by supernova feedback. And the fluctuation on the mass accretion rate are correlated with the bursty mode of population 3 star formation. In the simulated time of 120 mega-year, as you see on the top right panel, the black hole has accreted 1.5 million solar masses with an average mass accretion rate of 10 to the minus 2 solar mass per year, which is about 50% Eddington accretion rate. So properties of the host galaxy, as you see, the stellar mass in the host galaxy of this massive black hole is, by the end of simulation, is 10 to the 7 solar masses. The mode of population 3 star formation is very bursty, while the mode of pop 2 stars is rather continuous. The star formation rate in the host galaxy by the end of simulation are about 1 solar mass per year. We're also able to follow the stellar mass black holes from the collapse of massive stars in our simulation. We have about 70 stellar mass black holes, and none of them is able to grow because they are born in the H2 regions of massive stars, which shuts the accretion onto the black holes, and this is further prevented from the X-ray feedback from stellar mass black holes. So my message from this talk is that black hole was able to grow to 1 million solar masses in our simulation because this halo lies at the intersection of cold flows, which basically keep feeding the black hole. And also our basically simulations show that high resolution cosmological simulations are important to study the physics of black hole accretion. Thank you very much for listening. I'll stop here. If you are more interested in our work, please check our paper or drop me a message. Thank you very much.